Hello everyone, in this theoretical tutorial number 76 we will see that a translinear square root function can be used to transform this quadratic function represented by the red curve into a linear function represented by the dark blue curve. For the first part of the curve, the equation is alpha t square. We can obtain a linear function using the schematic of an ideal differentiator as shown. The output voltage will be 2 alpha t with a linear slope of 2 alpha as shown in the Vout versus time diagram. We can also use a square root function using a translinear circuit as shown. Since this circuit operates with current, we need to change the voltage to current, so the input will be I in equal alpha t squared. Since the output current I out equals square root of I in times I1, I out will be equal to the square root of alpha I1 times t. This circuit will also provide a linear function with a slope of the square root of alpha times I1, as shown in the I out versus time diagram. For the second part of the input signal, the equation is alpha times 2 minus t square. For this input equation, the ideal differentiator circuit will give Vout equal alpha times minus 4 plus 2t, which correspond to a positive linear slope as shown on the Vout versus time diagram. The ideal differentiator does not provide the desired output voltage. Now let's see the effect of the second part quadratic function on the square root circuit. The input current is equal to alpha times 2 minus t square, and the output current is equal to the square root of alpha times I1 times 2 minus t. This expression gives a negative linear slope of minus square root of alpha times I1, as shown in the output current versus time diagram. The output current curve for this second part is shown in dotted line. This is a second example of the very useful use of the translinear circuit with this specific translinear square root function. In this slide, I will briefly review how the square root translinear circuit works. We start with the basic 4-pole translinear circuit, which provides an output current equal to I in times I2 divided by I4. In the modified circuit, I4 is removed and Q4 and Q3 are biased with the same output current I out. We sum the VBE voltages to obtain VBE1 plus VBE2 equal VBE4 plus VBE3. We now see that VBE1 is biased by I in, VBE2 is biased by I2, and VBE4 and 3 are biased by I out. We now replace each VBE with the expression for its own collector current. Since log of A plus B equal log of AB, we obtain the expression I in times I2 equal I out times I out. Then I out squared equal I in times I2, and then I out equals square root of I in times I2. The sum of VBE is equivalent to the multiplication of the current linked to each VBE. Since the square root of the output current is equal to the square root of I1 times I2, we need to determine which current will be the DC current and which will be the variable input quadratic current I in. We have two possibilities. In the diagram on the right, we have chosen to use the current I2 as the DC bias current of 10 microamp. I1 will therefore be replaced by I in. The output current will be equal to I out equal square root of I in times 10 microamp. In the diagram on the left, we have chosen to use the current I1 as a DC bias current of 10 micro. I2 will be therefore replaced by I in. The output current will be equal to I out equal square root of 10 micro times I in. The current I in biases Q1 and must supply the bases of Q2 and Q4. Since I in starts with almost zero current, Q2 cannot supply the 10 microamp bias current without current supplying its base. The diagram on the right therefore doesn't work well. The diagram on the left is the best solution because the 10 microamp DC current is still present to supply the bases of Q2 and Q4 as well as the collector of Q1. When I first used this translinear square root circuit in this application, I encountered a problem related to the fact that we were working with an input current starting at almost zero current. Since Q2 always supplies the base current of Q1, Q2 can never reach zero. The minimum value of I in is equal to IB of Q1. Ideally, with I1 equal 10 microamp, for I in equal 0, I out should be equal to 0. For I in equal 0.2 microamp, I out is equal to 1.4 microamp. For I in equal 43 microamp, I out is equal to 18 microamp. It should be noted that the gain increases considerably as the input current approaches 0. For I in equal 200 nanoamp, the gain is 7 compared to 0.4 for I in equal 43 microamp. This high gain at low input current is visualized in the graph. The current gain Gi equal I out over I in increases from a gain less than 1 to a gain equal to 1 and then to a gain well above 1. The main problem arises as I in approaches 0. In DC operation, the output current I out should be very low, on the order of few hundred nanoamp, as indicated by the blue curve I out. In general, the 10 micro bias current is constant over time as indicated by the orange curve in the diagram. To reduce the minimum current in Q2, which is the base current of Q1, the only solution is to reduce the 10 microamp DC current that biases Q1. The solution I found was to maintain the 10 microamp bias when I in was greater than 1 or 2 microamp and to reduce it to 400 nanoamp in DC operation and when I in is lower than 2 microamp. The 10 microamp DC bias current is then no longer DC but is low when I in is low to ensure that the DC output current is not too high as indicated by the red signal. We will now examine the circuit diagram for changing the DC bias current from 10 microamp to 400 nanoamp if necessary. M out, M in and M1 have the same area and form a current mirror. M in is biased with a 10 microamp bias current reference. I pulse equals 0. When the 400 nanoamp pulse current IPLS is 0, the 400 nanoamp biases the mirror current MDIS in and MDIS. Since IPLS equals 0, no current flows through MDIS, which shorts the gate and drain of M1, as shown in the simplified diagram with the short highlighted in red. M1 then drives the 400 nanoamp, M1 and M0 form a current mirror, so the output current I out equals 400 nanoamp. Then, when I pulse equals 0 to 400 nanoamp, when IPLS is set to 400 nanoamp, the mirror current MCH in and MCH produce 800 nanoamp from both sources. MDIS pulls 400 nanoamp down. The remaining 400 nanoamp charges the capacitor C connected to the gate of M in, M0 and M1 hence Vg. The gate of M min rises linearly, then the drain current is quadratic as shown in the orange current signal. Now I pulse equal 400 nanoamp. When Vg is sufficient to allow M min to pull down the bias current reference by 10 microamp, the MCH shorts the drain to the gate of the M min. Since VDS of MCH equals 0, no current is present in MCH. The 400 nanoamp through MCH in flows into MDIS, and then no more current charge the capacitor C. Vg therefore remains at the voltage necessary to allow M min to drive the 10 microamp. Now I pulse equal 400 nanoamp to 0. When the IPLS drops from 400 nanoamp to 0, the discharge MOS MDIS discharges capacitor C with a constant pull-down current of 400 nanoamp, producing a linear negative slope on the gate of M in. The drain current is then quadratic as shown in the orange current signal. When MDIS shorts the drain to the gate of M1, M1 and M0 form a current mirror powered by the 400 nanoamp current, causing a 400 nanoamp pull up of the M out. Here is the complete circuit with a quadratic input current I in red, biasing the bipolar transistor Q2 and the collector Q4 providing the linear current in blue. The left part of the circuit allows the DC bias reference of 10 microamp to be changed to two bias current value 10 micro and 400 nanoamp, driven by the IPLS pulse command. I want to thank you for your attention. In my next TRICR tutorial number 77, I will review the integrator circuit. So see you soon and stay tuned.